Hello and welcome back. This is our first Friday. Today we're going to wrap up brute force algorithms and then move on to the next module or the next topic, which is divide and conquer style algorithms. So today I'm just going to, we've looked at all the algorithms or at least general approaches that we're going to cover. But I did want to cover two more problems because they are going to be used later on in the semester, and of course it gets us more practice thinking about how we can apply these kind of brute force algorithms to these very difficult problems. So first of all, a clique problem. I already previewed this last time. Remember, we are on Piazza. If you have any questions, please go ahead and post to the live Q&A there. I do have the chat going for YouTube. If there's any problems with the stream, please let me know. So more formally here from last time, given a graph G, right? And remember, a graph, it's an undirected graph. So it's always a two tuple, which is a vertex set and an edge set. A clique, or clique, some people pronounce it clique, some people pronounce it clique, is a subset of vertices, C of vertices, such that every vertex in C is connected, period, to another vertex in C by implication there, right? In other words, C is a complete subgraph, right? A complete subgraph, you know, a subgraph being like K1, K2, K3, where you've got, say, n vertices, and every vertex is connected to every other vertex. In other words, the edge set is as full as possible, okay? So the motivation here, as the name suggests, it dates way back before social networks, but you can find, you know, clusters of things. There's a clique, if you've got a very, very large graph representing relationships, you can find little clusters, and that could be represented as a clique. In other words, you could collapse that all down. One thing that you could do is take a very large graph, and then if you just want a representative of each one of those clusters, then of course you can contract the graph down into one connected component, right? And you reducing the overall size of the graph so that you can still do like meta-analysis on it or something like that. It also has applications in biology, dependency analysis, right? If you have a very large, complex software system where components depend on other components, you want to find out where, if it's, in general, what you want is a loosely coupled system. But if you have a highly coupled system where these things depend on this thing depends on 50 other things, and each one of those things depends on it, and vice versa within that group, then maybe that is a point where you want to redesign the system so that there's loose coupling and there's not such this huge dependency analysis, or finding dense subnetworks, right? In other words, it represents a lot of redundancy, a redundancy that may be good, it may be bad, and you want to eliminate that redundancy, or you want to simplify that redundancy because if, for example, you want to spread a rumor in a clique, right? You only have to tell one person in that cliquish group, and you're pretty sure that it'll get around to the rest of the group, right? When you're talking about in terms of networks, then you broadcasting to one node maybe, and that node rebroadcasts to the rest of them, something like that, right? So you can kind of get the idea here. The clique problem itself is given a graph, right? And maybe an integer k. Does the graph contain a clique of size k, right? Or another optimization problem, you're not given k, right? Given a graph, find the size of the largest clique or clique, right? You can also have functional versions where, all right, well, great, it has a clique of size k. Give me all those nodes so that I can do something with it. That's the functional version, right? So optimization, functional version, counting how many clicks of size k are there, et cetera, right? Just to illustrate, let's make sure that we are all on the same page. I did this yesterday, of course, but here's a graph that we've used before, and you'll note here that there is a clique, say A, B, D, right? Any triangle, like we did in our quiz yesterday, it represents a clique of size 3. Is there a clique that's larger than that? Not in this particular graph. But if we were to add some more edges here, say B to F, let me redo that. B to F, right? Nice and smooth. Then we do have a clique. That clique is of size 4 with B, C, E, and F. And as we add more and more edges, if we have a complete graph, then the entire graph represents a clique, right? I'll go ahead and erase that though, because that's the original graph. There are several cliques of size 3 here, right? There's a clique of size 3 right here. There's a clique of size 3 right here. There's a clique of size 3 right here, right? And that's just by nature of me drawing this nice, clean, planar looking graph with just 3 triangles in it. But again, the problem is you want to optimize this. You want to find the largest clique. Small cliques are common. In fact, you can have a trivial clique. A vertex by itself is always going to be a clique. And an edge and its 2 endpoints are always going to be a clique. You want the largest clique possible, right? So how do you approach this problem, right? Well, we could naively approach this problem by generating combinatorial objects, right? Naive approach. Right? Generate all possible. Now, think about this. We've already said that a clique here is a subset. So in the very problem statement, it tells you what kind of combinatorial objects you should be generating. We can generate all possible subsets, right? Verify that a subset is a clique, right? And what I mean by that is you have to look to the topology of the graph, right? If I took the subset A, B, D, right? Then how would I verify that that's a clique? Well, that edge is there, that edge is there, that is there, the edge is there. So yes, that's a clique of size 3. But if I have a different subset, say B, E, F, right? I could verify that B and E are connected, E and F are connected, but B and F are not connected. So no, this is not a clique, right? It does not represent a complete subgraph. Okay. So all you have to do is generate all possible subsets. And then finally, take the largest clique, or answer yes. If this is a subset of size k and it is a clique, great, you're done. If that's the the decision problem, right? Given a graph G and an integer k, right? The optimization problem, of course, would be you could start out with the largest possible set and test that. Does that represent a clique? No. Okay, well, take one of those vertices out. Does that represent a clique? No. All right, put it back in, take another one out, etc. You just try all these things. Or you could do a backtracking solution. It's still a brute force solution, but you could put a little bit more thought into the structure of the problem itself. For that, I would draw your attention to that tree that we've now drawn several times here, where you're generating subsets. Again, this is just an example, a small example on say a graph with 4 vertices labeled 1, 2, 3, and 4. Right? You would generate all of these subsets, and then each one you would verify. Is that a clique? Yes. Okay. Well, we know that there's a clique of size 3. Is that a clique? No. Then there's no clique of size 4, etc. Right? But when you're approaching this from a backtracking kind of solution, think about how you can exploit the structure of the graph itself. For example, suppose that I'm down here at A1, A2. Let's say that this represents the graph. Here's A1, here's A2, maybe A3 and A4, and the graph looks something like this. Okay. Now suppose that I'm over here at the subset A1, A2. In other words, I'm considering this set right here. Automatically, I know that that's not a clique, right? So what I could do is I could say that if I include A1 and A2, they're not connected. I don't need to consider any possible subgraph that contains both of those things as a subset. None of these things are going to be cliques because I was able to test that up here, and that consequently I can go ahead and trim out this entire subtree over here, right? But the idea, again, the idea is that that you add a vertex, and then can I add another vertex? A1 and A3, yes, those are connected, so keep going, right? And that's the idea. We're not going to go into the full pseudocode here, and sometimes I've assigned this as the programming assignment. I think they did last summer or something like that. But you get the idea. That's the better approach that would allow you to prune possibilities, right? So again, the idea is the better, or I'll say slightly better approach, because it's still going to be brute force. It's still going to be exponential in the worst case, right? Take the graph connectivity into account, right? If you build a subset that is not a clique, then do not consider any further superset of it, right? Here are my vertices, right? These 3 vertices, that's not a clique. Why would you naively go ahead and add more vertices into that, right? When you know that these are not a clique, it doesn't matter if this one's connected to all the others. These 2 are not connected, say. So why even add anything? Backtrack, right? Backtrack if that is the case, right? So that's the idea. And again, it's only slightly better because at least you are not naively doing blindly combinatorial objects, right? In fact, if you are doing the clique problem on the decision version here and you're given k, then there's no reason to generate subsets of size k minus 1 or k plus 1, right? You're just concerned with subsets of size k. And even that, in general, is not going to be polynomial, not going to be efficient, okay? All right, the last problem that I want to talk about is probably something that you have seen before, maybe from, say, 235, is at least you've seen the material for it, is satisfiability. So recall that a predicate is a logical statement using and, or, and negations on, say, n variables, Boolean variables. And usually we write these things as p sub, and I'll write this as a vector of x, right? Is equal to some predicate on x1, x2, dot, 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 xn. There we go. There we go. All right. And that's just a generic predicate. We're going to get to an example. In fact, let's look at examples now. Examples. Dot, dot, dot. So let's go ahead and transition over here. Here's an example, right? This is a predicate. Each one of these things, in case you're not familiar with the terminology, this is called a clause, right? Because it only has or statements here. That's another clause, that's another clause, clause, clause. And then each one of them is connected by a logical and. Of course, it could be more complicated than this, but this is clause normal form. No, I forget what the term is, but basically, you can take any logical statement involving predicates, like x1, x2, and x3, their negations, the negation of x3, along with or logical disjunctions, along with ands, logical conjunctions. And you can always get it in the form where everything is just a clause that is connected by a bunch of logical conjunctions. A clause is a variable and its negations connected only by disjunctions or statements. Okay, so that is a predicate. We'll come back to that example here. The satisfiability problem, or SAT for short, is given a predicate on n variables, does there exist an assignment of those variables, that is to true or false, such that the predicate evaluates to true, right? And these are kind of the exercises that you've done in your, say, 235 class. Let's go ahead and take a look at that predicate again that we were operating on here. There are three variables here. So to determine whether or not it is satisfiable is akin to drawing out a truth table. Right? So remember, oops, let me go ahead and go with that. X1, X2, and X3. Each one of these can be true or false. Usually we associate 0 with false and 1 with true. So I could set them all to 0. And now what's the value of this thing? Right? Well, if I set this to 0, this is 0, 0, 0. 0 or 0 or 0 or 0 is going to be 0, right? It's going to be false. And it doesn't matter what the rest of these things are. It's still going to be false because all of these things are conjunctions. False and anything is going to be false. Right? Well, what about another possible truth assignment? What if we set at least x3 here to be true, right? Then that means that this thing is going to be true. Right? Now let's look on to the rest of them. This is going to be false or true. Okay, so that's true. X2 is going to be false, and then X3 is negation, so that ends up being false. So this entire thing ends up being false, right? One clause being false kills us for this entire thing, right? So let me go ahead and get rid of all those and observe that this is still going to be false, right? 0, 1, 0, right? Again, this is going to be true. False, and then the negation of this ends up being false, so this is going to be false. We don't have to check all of the clauses. The first clause that we see that evaluates to false means that the entire expression, the entire predicate, is going to end up being false. And I'll save you all the details here. This is not going to be satisfiable. There will be at least one clause for every possible truth assignment that you can make that will end up evaluating to false. 1, 1, 0, and finally 1, 1, 1, right? 0 and 0, right? So we'd say that this is not satisfiable. Observe here that if we have n variables, then we have 2 to the n possible truth assignments. And that's because that's the number of bit strings of length n there are, right? Bit strings 0 and 1 can be associated with each one of these possible truth assignments. Let's take a look at another example here, right? A much smaller one, but let's go ahead, but it's still on 3 variables. So we'd have to go potentially through a whole bunch of 8 different truth assignments to find whether or not it is satisfiable. So let's go ahead and do that. So this one will make the first predicate false, so we can immediately say nope. 0, 1, 0. Or sorry, the next one will be, there we go, 0, 0, 1. That makes the first predicate, clause true here, because you're taking again a disjunction here. What about these? Well, x1 being 0, and then negation of that means that this is going to be 1. So we don't even need to look at the rest of this. This is also going to be 1. At least one of these variables or their negations has to be 1 in each clause. So it seems like an easy problem, right? So the negation of 0 is going to end up being 1, and so we have a value 1. We can immediately stop, right? We don't need to look at the 6 other possible truth values. This we're only looking at least 1, right? We're looking at does at least one truth assignment lead to a true predicate, and so this is satisfiable, right? Again, it connects to logic, right? This logical problem connects to logic. That it's basically this this problem is equivalent to determining if the quantified statement, and I'll put that onto the next line here. exists, right? Remember that that's the existential quantifier. Does there exist a truth assignment for x1, x2, dot, 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 xn, such that the predicate following it evaluates to true, right? And that is directly associated with satisfiability. You might have also remembered the other quantifier, the for all, which is kind of the dual of that. That for all truth assignments, the predicate comes out to true, right? But we won't pay attention. That defines a complexity class called co-NP. Eventually we're going to use this problem to introduce the notion of NP completeness. But I wanted to introduce it now in order to, well, first of all, so that you have exposure to it, but also to think about how might we approach this from a brute force solution, right? So what's the naive approach here? Well, you could say that, like we did tried to do in this exercise over here, generate the truth table and evaluate it on all possible truth assignments, right? Well, how do you do that? You generate all possible bit strings of length n, of which there are 2 to the n of them, right? Now, going back to what we've been discussing this entire time, what kind of combinatorial objects are there, right? So again, let's take a look at that truth table, the full truth table over here, right? What were we doing? We were generating these things, right? 0 is repeated, right? 1 is sometimes repeated, right? So we're looking at permutations of 0 and 1, but allowing for repetition. And we know how to do that because we presented how to do that. All you have to do is start counting, right? So you can do this by generate all permutations with repetition, right? And remember how to do that? You simply need to count. At least with binary, with any base system, all you need to do is count in that base, or count in integers and then convert to that base. We did that with DNA strings. You can do that with bit strings, right? What's the better approach? The better approach would be to generate what are called partial assignments, right? And if the assignment of a value to a variable makes the entire predicate false, backtrack, right? So if I'm walking along here and I suddenly decide, oh, set x2 to false, that makes one clause false and thus the entire predicate false. No, don't do that, right? So you don't have to consider, okay, fine, I'll set that to 1 instead, right? And that kind of backtracking approach is much better. Let me go ahead and illustrate it graphically over here, right? So if you want to look at it from the perspective of, again, recursion, what I'm going to do is I'm going to start at x1, right? And I have 2 choices for setting x1. I could set it to 0, or I could set it to 1. That sets up a partial assignment, right? If I set x1 over here to 1, right? Then basically it's no longer, oh, it's not that. There we go. 1, 1, and then this ends up being 0. These are no longer variables, right? What I've done is I've reduced the problem down to a satisfiability question on n-1 variables. Because once I set a value here to x1, and by implication, its negation will be 0, then that takes that variable out, right? If you've got an algebraic expression with 3 variables, and you set a, b, and c, and you set a to 10, guess what? You have you have an algebraic expression with only 2 variables, right? So you can ask yourself, if at that point, if either choice causes piece of x to be false, right, or true, and for that matter, stop. Actually, don't stop. Let me go ahead and split those two things out. If it causes it to be true, then stop and output yes, it is satisfiable. Right? It doesn't matter what those other variables are set to. Setting that one variable sets the entire predicate to true. Those other variables would be what we call free variables, right? You can set them to whatever you want. It doesn't change the value of the expression. If it ends up being false, then stop, or then backtrack. If I chose to set x1 to true, but then that killed the entire thing, stop. Okay, don't go down that path over there. Instead, backtrack and go down that path over there. Those aren't the only two possibilities here, right? It could be true, it could be false, or dunno. Right? It's still a predicate on n-1 variables now, but I don't know if it's satisfiable or not. I have to check the rest of the variables because it could be or it could not be, depending on what I set the other variables to, because those variables are not free variables. So I have to continue. x2 and x2, I have two choices there. I could set that to false, or I could set that to true, right? And you would continue this way. But you can imagine that if you ever get to a point where 3x3, if you ever get to a point where it's either true, then you're done. Yes, it is satisfiable, or it's false, and then you can backtrack. In other words, you can end up cutting out this entire subtree over here. And again, if you in the worst case scenario, you have to check them all. Just like this was the worst case scenario over here. I ended up having to write out every single one of these truth values in order to determine that it was not satisfiable. Whereas for this example, I got lucky, and on the second one, or one computational branch, I was able to say, yes, it is satisfiable, we're done, right? But you can imagine what the full tree would look like in the worst case scenario. This is a full tree. It's a full binary tree of depth n. Right? Why is it of depth n? Because you have n variables. You can set x1 to 0 or 1, x2, x3, x4, dot, dot, dot. So how big is it? How many leaves are there here? Well, there's going to be 2 to the n leaves, each one corresponding to one of these possible truth assignments. Okay? So that's the general approach. Right? All right. I don't see any questions so far, at least in the live Q&A. Again, if you're make sure that you're posting to the live Q&A if you've got questions during lecture here. Okay. All right. That effectively concludes brute force algorithms, or at least what I want to cover as far as brute force algorithms. Yesterday we had covered everything necessary for your first assignment, so make sure that you've gotten a good start on that before the weekend. Today's Friday. Make sure that at the very least you should have your parsing done on both of the programs and a good chunk of the written work done already. So that's just a little bit of a milestone there to make sure that you're ahead or behind or something like that. It's always good if you're ahead. All right. Let's start talking about our next topic here, which is going to be divide and conquer algorithms. All right, just switching modes here. There we go. So you've seen this approach before. You've probably seen binary search. You've probably seen quicksort and merge sort and other divide and conquer style algorithms. Basically, the approach is, and Sun Tzu or whatever, divide. You want to defeat an army, divide their forces, defeat the smaller part, and then then you can individually. You've destroyed half their army. You destroy the other half. It's much easier because you're bearing the full force of your army onto a half of their army or a fraction of their army. So you divide a problem into smaller problems, right? Until the problem is easily or trivially solved. With respect to merge sort, for example, if you remember that, you'd have an array and you need to sort it. Okay, well, I'll go ahead and split that into to 2 arrays, and then I'll worry about sorting this half. I'll split that into another half, and I'll worry about sorting just these 2 elements over here. And I'll split that again, and I'll only have to worry about sorting this 1 element over here. But guess what? Trivially, an array of size 1 is already by definition sorted, right? That's called the base case, right? You may then need to combine sub-solutions to produce a solution to the larger problem. With respect to merge sort, once I had these 2 arrays of 4 elements each, say, I had to merge them together. How do you do that? Well, you zipper them up somehow, right? You merge them by only going over each one element at most once. This one is less, so put that into the result. No, this one is less, so put that into the result. At the end, you've basically zippered them or merged them up together. That's why it's called merge sort. Right? We don't like to be too creative in computer science. If we already have a term or an obvious, what it says on the tin, kind of a name for something, we use it. Right? Usually, such approaches are presented as recursive, but they don't have to be. Binary search is a prime example. You can binary search if you've got a sorted array. All you have to do is jump to the middle. And is that the thing you're looking for? No. Okay, the thing I'm looking for is larger, in which case I go recurse on this size. Or if the thing I'm looking for is smaller, so I recurse on the lower half. Because it's already sorted, it must be in one of those other halves. That's usually how it is presented initially as recursive, but you don't need that, right? All you need to do is set up index values. I'm keeping track of the lower bound and the upper bound I and j, and I'll simply move those. And while I and j are still have represent a sub array of size greater than 1, right? I'll move them in on each other. Only when they've passed each other, that's going to be the unsuccessful search. If you need help with binary search, merge sort, and other stuff that's usually covered in, say, Computer Science 2, check out my other videos from CSCE 156. All right. So why do we like divide and conquer approaches? Even if they're not recursive, they're well suited for parallelization and distributed computing. Right? If you can split up a problem into 2 subproblems, you can farm this one problem out to one processor and farm this problem out to a different processor, and they can work in parallel. Meaning that you will get your answer in half the time plus whatever overhead it costs you. If you can do that, well, you can do that among 4 processors, 4 cores. If you can do that, you can do it among 8 cores. And then if you have an entire grid computing system with 600, 700 cores like they have over in HCC, the Holland Computing Center, then you can farm it out and get your answer in a fraction of the time. Right? And that's parallelization or distributed computing if you're parallelizing it among different computers. Right? MapReduce is probably the most famous or the most widely used kind of general framework for doing this. Right? And if you can get an account over at HCC and start writing, say, some highly parallelized merge sort algorithm and run it just as a lark over on HCC. But also searching and sorting, as I've already mentioned. Binary search, merge sort, quick sort, those are all divide and conquer style algorithms. And of course, it's very natural. It basically leads to tournament style strategies. Right? What do I mean by that? Well, let's go ahead and go back over here to, there we go, to the iPad. Now, even when I was in grade school, if I were given a list of numbers that I had to add up, say 8, 3, 4, 7, 2, 1, 5, 9, 10. Does that all fit? Yep, good. How would you generally go about this? Would you go, okay, 9 plus 8, that's 17. 17 plus 3, that's 20. Another 4, right? Okay, one by one, iteratively, adding one to the next and keeping track of the sum in your head. I never found that all that easy. So what I would do, especially on a piece of paper here, is I would set up a tournament. Adding two numbers and then just writing down the result is a lot easier than keeping track of what the running total is. Do that all over the place. And let me go ahead and get rid of that 10 because I won't have an even number to do this. I miscounted. And then 6, right? And then what you do is you apply that same idea even again, right? 23 and 15, and then finally 38, right? This is kind of a tournament style. You've seen brackets before. I think I can. Can I? Oh, I can't. I was hoping I could rotate it. Resize color. Okay. Copy. I could probably. Yeah, I can rotate the copy here, right? Or so you can look at this from a tournament style, which is what I wrote over here, right? The NCAA brackets, things like that, where one team plays another team and then that team is eliminated and then they go off to the loser's bracket or something like that. Or you can look at it as a top-down kind of thing. I want to know what is the total, right? Well, okay, I've got these numbers, split them in half, right? And solve that problem over here. All right, well, I don't know how to add 4 numbers, so split them in half. I do know how to add 2 numbers now, right? That's your base case. You simply add them up and return the results back up from each one of these sub-branches. I like this top-down representation because that is a divide and conquer approach that usually it has a good visualization. So what I want to do now is I want to get a little bit more practice in thinking recursively and thinking in a divide and conquer kind of approach. And to do that, we're going to do a problem that you're already well familiar with, which is linear search. Just making sure that everything is fine. All right, so let's go ahead and write a traditional linear search algorithm first to begin with. All right, just a second. First of all, I'm going to need some testing code here. So there we go. I just created an array here, and I've got a key. I want to search for that particular key in there, and I'm going to call this linear search algorithm, giving it the array, the key that I want to find, and by implication here, it's going to return the index at which it found it. If it's unsuccessful, it's going to return -1 because -1 is never a valid index, right? And then we're going to report our results here. So here's a traditional approach with the linear search algorithm. Def linear search, A and key. Right. How would you go about solving this problem? You'd set up a simple loop. And because I'm interested in the actual index here, I am going to set up a loop, an iterator variable loop for I in the range of the length of A. If I find what I'm looking for at index I, so if A sub I is equal to the key, I'm done. I've found what I'm looking for. I will return I. Right. Otherwise, if I get through the entire array, then I'll return -1. Right. There are variations on this. Of course, you could search for the last instance. You could search for all the instances, etc. But let's just make sure. Let's just make sure that this works. Oops. Python 3 demo. There. 0 was found at index 0. If I search for 42, I believe I'll find it at index 9. Yep. If I search for 5, I'll find it at 0, 1, 2, 3, index 3. Yep. And if I search for something that doesn't exist, then I get it at index 1. Right. That is a divide and conquer approach. So how could we think about dividing and conquering this and thinking more recursively? Ah, crud. You know what? Sorry, my apologies. All right, there we go. I was on the iPad the whole time. My bad. So if nobody either everybody's watching a playback or you haven't gotten to this point. Otherwise, please yell at me when I do something stupid like that. Anyway, here's the linear search algorithm. It takes an array, or a list in this case with Python, and a key that you're searching for, and then it goes through a traditional loop here. If you find the key at index I, then you return the index at which you found it. So we're finding the first instance, and then it returns -1 in the event that it does not find what you're looking for. All right? So how can we approach this from a divide and conquer approach? I'm going to look at two ways of doing this. What I'm going to do is first of all, I'm going to think inductively, right? That consider that we have this array of elements, right? And when you think inductively, when you think divide and conquer, or when you think recursively, you jump to the middle, right? So suppose that I am currently at index I, right? That I've already searched this half, or all elements up to A1 up to A sub I minus 1, right? And unsuccessful. I haven't found what I'm looking for, right? So I'm looking at A sub I right now, right? And I ask the question, is A sub I equal to the key? If yes, stop. Right? And output I. That's the thing that you are looking for. Right? Otherwise, how do I set myself up inductively for the next step? Remember induction. That you have a statement and it's true for K, or let's say that it's true for I in this case. I want to set that up so that it implies that it's also true for I plus 1. How do I set myself up for the next recursive call, basically, right? What I'm going to do is else here, search A among indices I plus 1 through n. In other words, this half of the list, right? We haven't searched that yet. So by writing it out like this, I've identified several things that I need to do this recursively. The current index, instead of a traditional for loop that's keeping track of that index, we'll pass it along recursively each time. We, of course, need the entire array, and we need the key. But otherwise, all we're going to do is make progress by moving along in our recursion one step at a time. So let me go back to my coding environment over here, and let me create another function, def linear search. I'll call it recursive, REC for short here. I still take the array and the key, but in addition to that, I take an index, and we called it I in my notes, so let's just call it I here, right? That's all I need, right? I represents the current index. Check it. If A sub I is equal to the key, then we're done. Return I. Otherwise, else if, actually just else. All right. There's no other. There is a possibility coming up here. Otherwise, what I need to do is I need to search the subarray starting from I plus 1. Right? Well, how am I going to do that? I call the same function. I'm not changing the array, so A. I'm not changing the key, but I am changing the index. Go to I plus 1. Right? Now let's go ahead and try this. Actually, where do I start out? So induction, you do need a base case here. Where do you start? I will start at index 0 because at one end. All right. So let's go ahead and run that again. Right. Uh-oh. List index out of range. What did I forget? Here you need a base case. There are 5 elements, say. That's not it, that's not it, that's not it, that's not it, that's not it. Keep going, right? You need a way to stop. So we also need a base case here. If I is greater than or equal to the length of A, greater than or equal to, because if it's equal, remember it's 0 indexing, then we want to stop. Right? Return, here's where my unsuccessful search happens. We got all the way to the end of the list or the array, and we didn't find what we're looking for, so we end up returning -1. Right? Let's try that again. Oops. Oh, you know what? I screwed up. We actually have to return something. You can't just call the function. So return the results of the linear search using recursion. Right, there we go. There, 41 found at index -1, unsuccessful search. We can search for 42 and get the same result as before at index 9. Oops, sorry. Key index. I screwed up. Let's see. Oh. Duh. The index at which you found it. There we go. Now that's all correct. Right? 42 is found at index 9. So my 2 mistakes there were not returning the result of the method call, and then of course not returning anything here at all. It ended up returning none, which was not an index. Okay. All right. Well, this is a nice decrease and conquer kind of approach, where you've got an array of size n. I don't know how to search that, but I do know how to search, the first element. That's not it. Okay, well, I've reduced the problem. I've reduced it down to an array of size n-1. Hand that off to me again. Okay, well, I don't know how to do that, but I can look at the first element, which now is the second element. And I do that over and over and over again until I get down to, okay, it's an empty array. I know how to handle that. It's an unsuccessful search, right? But we're only decreasing it by 1 each time. Another way of thinking about this is to like the Sun Tzu's army idea, where you are dividing the entire army into the enemy's army into 2 sub armies. Okay, what does that look like visually? 8, 4, 7, 3, 2, 5, 1, 42. All right, there we go. There's my array. That's too daunting. I don't know how to search an array of 8. But if we split it out into 2 arrays, 8, 4, 7, 3, and 2, 5, 1, and 42, right? Well, okay, that's a little bit a smaller problem. That's more manageable. But let's go ahead and continue doing that. 8 and 4. And then finally, down into, it's trivially easy to search an array of size 1 for the key that you're looking for. So I can go ahead and say, well, if the key is, if it's equal to the key, then return true. If it's not equal to the key, then return false. Right? And you have to be careful here about how you combine your 2 solutions, right? Here's my, I've come back from the recursion here, right? I'm right here. All right, I went down that direction and I asked, does that half of the array contain the key that I'm looking for? Yes. Okay. I don't even need to look at that half. I'm done. Thank you. Yes, it does exist. No, it doesn't. Okay, then I have to look at that half of the list. Right? Now let's go ahead and codify that in Python here. Right? So there's a linear recursion. I'll call this version 2 or something. All right, there we go. Just a moment. No questions so far, so we're good to go. All right. Actually, let me go back to my visualization over here, and let's find out how we can do that. It's going to be very, very similar to how you do binary search. Let's think about it inductively in general, right? What I'm going to do is I'm going to, well, here. I don't want to look at the middle here. What I want to do is I want to split this in half. And initially, this is going to be index 0 up to, I'm going to call this m. And this is going to be m plus 1 up to index n minus 1. Right? That's on the first one. How do I get this m here? Well, I can do n minus 1 divided by 2, something like that. And of course, you'll need the floor in case that it's a fractional number. But how do I do this in general, right? If I am at some point in the recursion and I've got I and j, right? Think about this more generally, right? I'm looking at in fact, I'm not even going to call it I and j. I'm going to call it left and right. How do I get this the middle index here, right? M, so that I can split it between m and m plus 1. All I need to do is a little bit of averaging, right? If you've got two numbers on the number line, how do you find their midpoint? It's their average, right? So L plus R all over 2, and then of course you need to make sure to take the floor or the ceiling. It doesn't really matter, so that if it's like 3 divided by 2, there is no index 1.5. You need to make sure that you have a valid index, right? So once I've split it out into L up to M and M plus 1 up to R, then I can recurse. I can hand this off to a recursive call, hand this off to a recursive call. So let's do that as a first step here. My version 2, I'm going to want to keep track of two things now, left and right, and of course still the key. I'm going to compute M, and to get the floor, I'm just going to use the math library. Floor, got to spell it right though. L plus R divided by 2. Make sure that you're putting parentheses where they need to. Now, right now I am committing a very, very bad operation. L plus R divided by 2, that's the mathematical way of thinking about it, taking the average. If you put on your computer scientist hat for a second, you'll see that this is very susceptible to overflow. If you have a very large array, say a trillion elements, and you're looking at L and R way down over here at the end, where this is about 1 trillion and this is 1 trillion and 1 or something like that. Let's go up 2 trillion elements. It's 2 trillion and 2 trillion and 1. You add those two things together and you have potential overflow for a 32-bit signed integer, right? But this is Python. It's just a toy example. I just want to draw your attention to it that in a real implementation, I would not do something like this, right? We need a base case. What happens when L and R have gone past each other? I suppose I could have done that first. If L is greater than R, then we have, come on, there we go. R, bad code completion in Atom.io today. I don't know why. There we go. Then we've reached an unsuccessful search, so I'll return -1. Right? That may not necessarily be necessary depending on how we do the rest of this function here. But I want to split it up from L to M, and then M plus 1 up to R. So I'm going to make two recursive calls here, at least initially. A and the key are unchanged. L up to M and an inclusive. And linear search recursive 2, A, the key is unchanged, but now we go M plus 1 up to R. Right? I need to do something with those results though. First of all, I need to capture them. If I go down that computational path and it says yes, here's the index, versus going down that computational path if it's unsuccessful. So let's just focus on the first one here first. I'm going to capture the index. Index is equal to that linear search. If it finds what you're looking for, you're done, right? If index is greater than -1, then return index. I don't need to search the other half of the list. That element that I'm searching for, key, is over here in this half of the list. Forget about it. Don't even bother looking at it, right? Otherwise, if it's not -1, if it's greater than 0, we still want that if it's the first one. Otherwise, we do need to call this, and we can just return that. If it happens to be -1, -1, and -1, well, I didn't find it, -1, right? It was an unsuccessful search, right? So this is searching the left. Search the left side. This is if successful, stop, return the index. Right? Otherwise, and I don't need an else here because the return will take care of that for me. Else, search the right side or right half. All right. Now I don't think that this is complete, but let's go ahead and try it. Iterative debugging here. 42. Yep. Okay. So position. Oh, that's because I never called it correctly. So if I'm going to call this, then I need the length of a -1. Right. There we go. All right. Still bad. Maximum recursion depth exceeded in comparison. Cool. That is a nice message there. Let's go back to the first version that I just described right here. What's another reason that you might not want to do it like this? Again, the whole in CS1, CS2, I discourage recursion in practice for this very reason. What if you had an array of size 10 million? Right? Think of what you're doing in your recursion. You're creating a stack frame. You're creating 10 million stack frames in your recursion. Now there are ways around that using Taylor recursion so that it optimizes and does not create. It reuses the stack frame over and over, but you have the risk of a deep recursion here. Even an array of size 1 million probably would not work in this case. I had meant to set up a demonstration of that, but I forgot to do it. I meant to set up a demonstration and have a randomly generated array and then do an unsuccessful search on it to show you that the recursion will end up, with a stack overflow. But I'm glad that it happened here too, because we forgot our base case, right? So, in fact, we forgot our no, we didn't forget our base case. We forgot our successful search case, right? So for example, let me go ahead and come back up here and rethink this. We actually need to check something, right? Is this the thing that we're looking for? So there are a couple of ways of doing it. A separate base case here would be if the L is equal to R, right? That means that we're only looking at an array of size 1. Okay, now we need to check it. If A sub L or R, they're equal, so it doesn't matter, is equal to the key that we're searching for, return L or R, it doesn't matter which, right? Else if, elif, ELIF in Python, there's no else in Python. Oh, there's no else if, excuse me, of course there's an else. But I think that will take care of what we need now. And that's why I was saying that this is probably not necessary. In fact, I'm going to go ahead and comment it out. Oop, nope. Comment. Nope. I don't know how to toggle comments in Python. So we'll just do it manually here. There we go. I don't think that that's necessary anymore now that we have this other base case. Still, okay. We're searching on MMM. We're searching L to M, L to M, L to M. Only 10 of you are online to help me out, so maybe I do need to restore this. Right? I do, because I do need an unsuccessful search, so I do need this. Sorry. Still. Okay. Let's see. What's going on here? If L is equal to R, if A is equal to K, return L. Else if left is greater than right, then we're done. I've screwed this up somehow. I know we can fix it though. We'll go ahead and make this into our other base case, and then we'll check m here. So if a sub m is equal to the key, then we'll return m, right? Without recursing at all. I think that this will work, but I'm not sure. Nope, still. What's going on? Recursive search to, darn it. I don't need m anymore. So I can go from L up to m minus 1 because I'm checking it up here. And then m plus 1 up to r. There we go. All right. But that's only one case that it works for. We need to test some more. Let's test another extremal case at the other end. That works. Let's test something in the middle, say 3. That'll be 0, 1, 2, 3, 4, 5 is what we expect. Index 5, okay. And let's check for an unsuccessful search. 101. Yep, there we go. All right. All right, and at this point I forget even what the last mistake I corrected was. I think it was this one. I changed it from if L and R have met, then go ahead and check to see if that's the thing that you're looking for. Oh, I probably didn't have an else statement. That's it. Here's another way. So I'm going to leave this because it works. But here's what I had originally. If L is equal to R, then I need. Then I'm done. Then I've got an array of size 1. What I need to do is if A of L is equal to the key, that's a successful search, right? Otherwise, there's no reason to continue. Else, return -1, right? You're down to an array of size 1. You simply need to return that value, right? So live debugging session here. Right? You guys aren't helping me. Come on. Let's see. I don't know how many folks are online. 13. Okay. So about, I think that we're at 32 enrolled now. So about a third of you are watching it live. Great. Good for you. Hopefully the rest of you are watching it, the recordings afterwards, or using some other semesters' videos. There we go. All right, so we've got plenty of practice here in thinking and implementing recursive algorithms here. What I wanted to do with the remainder of our time is introduce, and also remind ourselves, here, there we go. I'll save that for next time. Remember the master theorem? If not, we'll revisit that later. But what I want to do is I want to demonstrate a problem here that you have to think about doing it in a divide and conquer kind of approach. So it's a very, very simple problem. What I'm going to do is I want to compute a to the n, a to the n mod m for some a, n, and m, right? So in other words, what I want, let me go ahead and just write out the math if you really want to. Hopefully everybody is familiar. There we go. Hopefully everybody is familiar with these expressions. A to the n mod m, right? And the values that I'm going to use are, bear with me for a second, everything is slowing down to a halt. Hopefully the audio is still good. Let's suppose that A is 7, N is 100, and M is 17, right? To keep M small. What we're doing is we're 7 raised to the power 100, which is huge, right? More than the known atoms in the known universe, blah, blah, blah. But by keeping it mod M, we're keeping it small. In this case, 17, the value will have a range of 0 to 16. I don't know what the answer is. We go ahead and look it up on Wolfram Alpha. it will be able to compute this in a matter of milliseconds, right? It'll be something small, I think 8 or 12 or something like that. What I want to do is I want to write some Python code here to compute that for me. Right? So let's do that. But we're going to be naive about it. Right? In fact, what we're going to do is implicitly design a brute force strategy. N was 100 and M was 17. So you can use native code in Python to do something like this. I think you can actually use the caret. Don't quote me on that though, or something there similar there. The mod is the same modulus operator as in most programming languages, the %sign. But I'm going to do this in a naive way. So, what is the naive way? Naive way would be, all right, 7 times 7 times 7 times 7. How many times? Well, there are going to be 100 sevens, right? So in other words, 99 multiplications. That's not that bad, right? And then with modular arithmetic, you can go ahead and take the mod of intermediate values. So you don't have to take the mod all the way at the end, right? Like compute 7 to the 100 million and then take the mod. You can go ahead and go 7 times 7. Well, that's 49. Mod 17. That's the remainder when you divide by 17. That's going to end up being 15. And then you can multiply by 7 again and take the mod 17 ... right? In code, we're going to do something very similar. Right? So I'm going to start my result at 1, because if I started at 0, then 0 times 0 times 0 times 7 times 7 times 7, you're not going to get anywhere. All right, I'm going to set up a for loop for I in the range of up to n. Right? What I'm going to do is take the result times a, and then intermediate mod m. Right? Does anybody look up the actual answer here? If not, I'm going to have to do it. And then I'll print it out. Right? And I'm not going to type out all this code. I'm just going to steal what I had before. There we go. And let's run this. 4. I'm going to check Wolfram Alpha just to be sure. You can check along with me. I'm doing it on this computer because my computer's, my broadcasting computer is already grinding to a halt. Yep, 4. And that was pretty quick. It was both quick on Wolfram Alpha and it was quick here on my local computer. But now let's go ahead and mash the keyboard. There we go. By the way, Python does support, Python 3 natively supports multi-precision numbers. So even though this is bigger than 2.147 billion, the maximum value that it can be held by a 32-bit assigned integer, Python is okay with this. You pay a price for that. It's all done in software though. All right. Well, I've got a lot of stuff to do this weekend, so I'll go ahead and leave it broadcasting like this. Even if I did, there's no way that this is executing even in a week, maybe a month, probably years for this, right? Let's go back. We'll let it keep going. Why is that the case? Well, whatever this insanely large number is, that's the number of multiplications you end up doing, right? If this were 2 billion instead, you'd end up doing 2 billion multiplications. As it is, we're doing, I don't even know what the name for this would be. There's millions, there's billions, trillions, quadrillions, quintillions, sextillions. So 834 sectillion multiplications, right? Good luck with that, right? The naive way of doing this is not going to work. We need a divide and conquer strategy. I'll keep letting that operate there in the background. Hopefully it's not slowing everything down. But let's think about this a little bit differently. Again, divide and conquer, tournament style thinking. The way that I was doing this was by saying, okay, well, I'll have a different value here. What if it was 64, a to the 64, and then I'll leave out the mods so that it's just simpler, right? I don't know how to do that. So let's split that up into two problems. Right? A to the 32 and a to the 32. Why does that help me? Well, if I've got a to the 32, the result, a to 32, sorry, a to the 32 times a to the 32, guess what? You end up adding exponents because you've got a common base there. So a to the 64. That gives me my answer. In other words, all I need to do is go down and compute a to the 32. I've divided the problem in half by dividing the exponent in half. And go down this, potentially go down this way. And once I've got an answer from this recursion and an answer from this recursion, all I have to do is multiply them together. There's nothing to stop me from continuing that. A to the 16, a to the 16. There we go. A to the 8th. I'm not going to draw them all because I'm going to draw something else to your attention. A to the 4th, a to the 4th, a squared, and then a times a. And that's the base case when you're done. You don't need to go any further there. When I present recursion, I usually present, everybody always usually presents the first recursive function is the Fibonacci sequence. I like that and I hate it. I hate it because it's a kind of an artificial example. Why are you computing Fibonacci sequences? Do something useful. But it's also it's a useful as a bad example because it shows you how much redundant computations you're doing. That the Fibonacci of if you're computing Fibonacci of 50 recursively, you end up computing Fibonacci of 3 billions and billions of times, right? Why do that? Save that value off and reuse that value. That's where I introduce usually memoization, something that we'll talk about when we come to dynamic programming. In this case, I can also see a lot of repeated computations. A to the 16, a to the 16, a to the 16, a to the 16. Why would I go about computing that 4 times? Compute it once and you're done with it. Save it. Right? You don't need to compute this huge binary, this exponentially sized binary tree. That's what we were doing in our Python code, by the way. We were doing a. Look at the leaves when you get down to this bottom here. A times a times a times a dot 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 dot. However many times it takes. That's exponential, right? And that's why it's not. It's still running here. It hasn't even gotten to an answer yet. Save these computations, right? I only need to take a and save it once. Oh, a squared? Oh, save it off. A to the 4th? Save it off. A to the 8th, 16th, 32, 64. And what I've done is effectively cut out all of these branches, right? And the depth of this tree is linear. That gives me an idea. I don't need to do this recursively at all. If I do a bottom-up solution, observe these numbers in sequence. A squared, a to the 4th, a to the 8th, a 16, 32, 64. How can I reuse these values, but also not have to call these recursive, make these recursive calls? Right? Well, let's make one observation. A squared is equal to what? A times a. Right? In other words, it's a square. Once I've got that, what is a to the 4th? The next thing that I need to compute here in this tree. I need to compute a to the 4th. Well, what is that? That's a squared times a squared. In other words, it's a squared squared. If I just take this value and square it again, that's only one multiplication. Let's look at it again. A times a, right? That gives me a squared. That's one multiplication. Now, use that same value and square it again. That gives me a to the 4th with one additional multiplication. Use that value again. A to the 4th gives me a to the 8th. One multiplication. dot, dot, dot. Ultimately, how many multiplications do I end up doing? 1, 2, 3, 4, 5, 6. Instead of 64. In general, you only do log n, log base 2 of course is always implicit, multiplications instead of n, right? And you might be thinking to yourself, well, wait, I mean, that does look like a good improvement, right? Going from n to a log log n, that is an exponential speed up. But you know what? I've been Burke has been telling us that linear algorithms are great. That's not a linear algorithm. Again, this is an exponentially sized tree. Often students, or often even mature computer scientists, will make this mistake of skipping step 2 in my 5-step algorithm process. You identify the input. Step 2 is you identify the input size. The input size of a number n, right, is not n, right? It is log n. This is actually linear with respect to the input size. This is not. This is exponential with respect to the input size. And if you want to learn more about that, again, review my 156 material on algorithms and algorithm analysis. Okay? But there's more. What if I don't have a nice little power of 2 that divides everything? A to the 77, right? You can still break it down with respect to powers of 2. This is a to the 64 times a to the 8th. Yep, a to the 8th times a to the, that's going to be 72. So I need 4 and a to the 1st. Those all add up to 77, right? 12, 76, 77. Yeah, there we go. I'm missing things, right? What about a to the 32? What about a to the 16? What about a to the squared, right? You still compute these things because you need them to, you need a to the squared to compute a to the 4th. You need a to the 4th to compute a to the 8th. You need a to the 8th to compute a to the 16th. A to the 16th to compute 32, and that finally to compute 64. You compute them, you just don't use them, right? Once you're done with them, you throw them away. And that's the idea behind what's called repeated squaring. Right? What I'll do for the remainder of our time here is we'll develop this pseudocode together. Right? It's in the notes if you want to skip the rest of this and get to work on your actual assignments. But you will need to ultimately program this in Python or whatever programming language you're using. You will not be allowed to use the built-in operations, which are obviously going to be a lot more efficient and actually run. Right? There we go. So, repeated squaring. There we go. So my input will be integers a, n, and m. The output will be a raised to the power n mod m. And again, the only reason we include mod m in there is so that we don't have these ridiculously large numbers, with 50,000 digits or something like that. By taking a small modulus, we'll end up, with a small manageable number that we can then compare to our answers. Right? All right. So what I'm going to do is I'm going to keep track of what's called a term. Right? This is similar to what I did with the naive approach that's still running in the background, by the way. In that you have to start somewhere. Do you start at 1, or do you start at a itself, and then multiply by a, multiply by a? Right? What I'm going to do is I'm going to convert n to binary, or consider its binary form, and I'm going to label those as bk bk minus 1, oops, bk minus 2 dot 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 down to b naught, yeah, b1 and then b0, right? Those are the bits, right? This is also called binary exponentiation because we're using the binary representation here, okay? So I need to start out my product. Right? If the first bit is 1, then that means that basically we are it corresponds to a to the first, right? This right here is b naught, right? If it were b, if we didn't have this expression here, right, it would be a to the 0, which is 1, and that's what I'm setting up right here. So my product will end up being a, else my product will end up being 1, right? Because it's a to the 0 basically, and we're not going to use it's like this expression, but we would end up being ignoring this term right here. Right? All right. Now I just go into a for loop. For I running from 1 up to k. Observe here, we're starting at the lowest order bit, and then we're moving up to the highest order bit. That's why I labeled it as 1 through k. If you convert to binary explicitly to like a string or something, that's fine. There are better ways of doing that using bit twiddling that I won't go over, but bit shifting and stuff like that, and masking. But if you need to think about this in terms of binary strings, that's perfectly fine too, right? But you need to start at the proper end, the lower order bits. Okay. What we're going to do is we're going to take our term and square it. Term squared mod m, right? Again, that's us doing this. A squared, a squared, a to the 4th, a to the 8th, a to the 8th, 16th, 32, 64. Basically, we're computing this tree from the bottom up, but only this one branch. Okay? Hopefully it's not bad enough that the entire thing is so somebody says that the audio is really bad. It looks like it's lagging a little bit. Yeah, a little bit. Hopefully that clears up. If not, then we can go over this again on Monday. Anyway, to complete it out, then we take that bit into account. If b sub I is 1, then we include that term. Otherwise, we don't include that term. So product will end up being product times the term. And then here you can also take the mod m. Right? And then at the end, you output the product. Right? And obviously, I'm not going to program this because that's part of your assignment. But that's the idea, right? You only there is no else statement right here because if the bit is 0, you still compute the term, but you end up ignoring it, right? We ended up ignoring A2, A16, and A32. Okay. I'm going to go ahead and end it there because the audio does seem to be lagging quite extensively. But otherwise, make sure that you are working on your assignment this weekend. It is due on Monday at midnight. If you have any questions, please come to office hours today, every day. My office hours, again, are 1 to 2. Sarah's here at 3 to 4, and we'll see you there. By the way, it's still running. All right, have a good weekend.